Okay, so in previous session we have derived the expression for the maximum deflection on the beam is shown here. So from this expression, if we know the expression for if we know the value of Q, L, E, I, then we can come out to the numerical value for the deflection. So in this question, we got we know the uniform distribution Q, we know the span, we know the E, but we don't know the moment of inertia. Instead, given the moment of inertia, this question gives the maximum bending stress sigma. So here we try to, based on this information, to find out the moment of inertia. So I just write down the value over here. So we know Q, we know the span, we know E, we don't know the value of the moment of inertia. We know the maximum, this beam maximum strength, the material of this beam, the maximum stress is 60 megapascal. So as we know, this beam is the cross section of this beam is a square. So it's a square. So the dimension is A. So for this square, we know the moment of inertia is A to the fourth power over 12. So this is the expression for this beam. And we also know on this beam, we know the bending moment diagram is like this. The maximum bending moment diagram is on the mid span is QL square over 8. So this is maximum bending moment. The maximum bending moment. Once we know the maximum bending moment, so if we cut the beam at the mid span, the mid span we know, if we cut through that, we know the stress distribution on the cross section is like this. So this is a neutral axis. So at the mid-span, we have maximum bending moment. On this mid-span cross section, the maximum stress is on the outer surface, is either over here or either over here. Okay, this is maximum stress. So if we can calculate the maximum stress and make sure this maximum stress not larger than this value, then we can find some relationship between the maximum stress and the moment of inertia. So how to express maximum stress? So as we know, based on the strain and curvature relationship, we know the strain can be expressed by y over rho. Rho is the radius of curvature. So y is a location. Y is a location from the point to the neutral axis. This is y. Rho is the curvature. Most of all, we just deal with the elastic material. So we know we can apply Hooke's law. So we know the stress is equal to Young's modulus times the strain is equal to Ey over rho. So this is expression for the stress. We know the moment curvature equation is mx over ei. So this dy over dx squared is just 1 over rho. Okay, so we just plug in this one. We got stress is equal to Ey over O equal to Ey times the mx over ei. So we can cancel this 2e. We got the expression for the is mxy over I. Okay. So we know at the midspan we have the maximum bending moment. Maximum bending moment is equal to QL squared over 8. So we can calculate that is 1 kilonewton meter. So this is the maximum bending moment. And the y, the maximum stress on the cross section is the outer surface. The outer surface, the y, is equal to a over 2, because we know the dimension of this cross section is a. So the outer surface is just half of the dimension, 1 over 2. And we know I is equal to a fourth power 12. So if we just, then we can just plug in these two into this expression. We got the stress is equal to maximum bending moment a over 2. This is maximum stress, so a force over 12. We got 6. Okay, so maximum stress have to less than 60 megapascal. So we know the maximum bending moment is 1 kilonewton meter. So then we can calculate a cubed. The value for a cubed is equal to 1.0 times 10 to the negative fourth power. So this is the dimension of the value for a. Once we know the value of a, we can calculate the moment of inertia is a4 over 12 is equal to 3.87 times 10. So this is the moment of inertia. Once we know the moment of inertia, so we know the Q, we know the L, we know E. Now we know the moment of inertia. So we know the maximum deflection is equal to 5QL to the fourth and 384 EI. So we got 5 is 2 kilonewton per meter, and is 2 force meter fourth, and 384 times 70 G Pascal, and 387 times. Okay, we just put the unit on this expression. Once we do some calculation, we can calculate the deflection is approximately equal to, this is about 15 millimeter, and the direction is going downwards. So this is maximum deflection for this beam. Okay, this is the whole solution. Thank you.